You think you understand time. You think you know why yesterday is different from tomorrow. You watch a cup shatter on the floor and you think, obviously it can't put itself back together. But have you ever asked why? Not just accepted it. Actually asked. Because here's the thing that should disturb you. The laws of physics don't care which direction time goes. Every single equation, every force, every interaction works perfectly fine backwards. So why doesn't reality? Why can't you unscramble an egg? Why can't you remember tomorrow? Why does everything fall apart instead of coming together? That's not an answer you've been given. That's just something you've accepted because it matches your experience. But accepting something isn't understanding it. And when you actually dig into what's happening, when you trace the question all the way down to its roots, you discover something so strange, so fundamentally unsettling about the nature of existence that it changes everything you think you know about reality, memory, causation, and why the universe is the way it is. Let me show you what I mean. Drop a cup on the floor, watch it break. Pieces scatter everywhere, sharp fragments, dull thuds, the sound of something irreversibly destroyed. Now sit there and wait. Wait for the pieces to jump back up. Wait for them to fly through the air and reassemble themselves perfectly in your hand. You can wait as long as you want. It's not going to happen. You know it's not going to happen. Everyone knows it. It's obvious. But why? Most people, if you push them, will say something like entropy, or the second law of thermodynamics, or that's just how nature works. But that's not an answer. That's just repeating words. That's like asking why things fall and someone saying gravity, as if that explains anything. Richard Feynman understood this distinction. He spent decades thinking about what it actually means for time to have a direction, and what he discovered should break your brain. If you've never questioned this before, you're not alone. But now that you're seeing it, there's no going back. Once you understand what's really happening beneath the surface of every broken cup, every fading memory, every moment that slips irretrievably into the past, you'll see it everywhere. And you'll wonder why most people go their entire lives never really understanding the deepest mystery of existence. Here's where it starts getting strange. The phenomena of the world are evidently irreversible. Things happen that don't happen the other way. You drop a cup and it breaks, and you can sit there a long time waiting for the pieces to come together and jump back into your hand. If you watch waves breaking at the sea, you stand there and wait for the great moment when the foam collects together, rises up out of the water, and falls back further out from the shore. It would be beautiful. It would be extraordinary. And it never happens. The demonstration of this in physics lectures is usually made by taking a section of moving film, showing various phenomena, and running the thing backwards. The audience laughs. That laughter means something profound. It means this isn't going to happen in the real world. We know it instinctively, viscerally, in our bones. But that's actually a weak way to express something so obvious and deep as the difference between the past and the future. Because even without any experiment, our very experiences inside are completely different for past and future. We remember the past, we don't remember the future. We have a different kind of awareness about what might happen than we have of what most likely has happened. The past and future look completely different psychologically. Think about the words we use: remorse, regret, hope, anticipation, fear of what's coming, nostalgia for what's gone. These words distinguish perfectly obviously the past from the future. You feel you can do something to affect tomorrow, but none of us believe there's anything you can do to affect yesterday. Now, if the world of nature is made of atoms, and we too are made of atoms that obey physical laws, this obvious distinction between what happens in the past and the future, this obvious irreversibility of all phenomena, you would think the most likely explanation is simple. Some of the motion laws of atoms must be one way. The atomic laws must not work in both directions. There's somewhere in the fundamental machinery some principle that makes things only work one way and never the other. That's what you'd expect. That's what seems reasonable. And it's completely wrong. In all the laws of physics that we've discovered, there doesn't seem to be any distinction between the past and the future. The moving picture should work the same way going both ways. A physicist watching the film should not laugh. Let me show you exactly what this means. Take the law of gravitation as our standard example. You have a sun. You have a planet. The planet orbits in an ellipse sweeping out equal areas in equal times, exactly as Kepler described and Newton explained. Now take a moving picture of this orbital motion and run it backwards. What happens? The planet still goes around the sun in an ellipse. The speed is still such that the area swept out by the radius is the same in equal time. It does exactly what it ought to do. Perfectly satisfactory. You cannot distinguish it from the one going the other way. The law of gravitation is such that it doesn't make any difference if you show any phenomenon involving just gravity running backwards on film. It looks perfectly acceptable. Put it more precisely this way. If at a given instant all the particles in a complicated gravitational situation had every one of their speeds reversed suddenly, then the thing would just unwind through all the configurations it wound up into. If you have a lot of particles doing complicated things, and you suddenly reverse all velocities, they will completely undo what they did before. This is built into the structure of gravitation itself. If you reverse time, the forces don't change, and so the changes in velocity aren't altered at corresponding distances. Each velocity has a succession of alterations made in exactly the reverse way they were made before. The law of electricity and magnetism, time reversible. The laws of nuclear interaction, time reversible, as far as we can tell. The laws of beta decay, also time reversible. There were some experiments suggesting possible violations, certain exotic processes that might distinguish past and future at the subatomic level. But even if those exist, they're completely irrelevant to everyday irreversibility. The possibility of speaking, of voices traveling through air, of cups breaking, none of that depends on exotic particle physics. It depends on chemical interactions, electrical forces, gravitation, and all of those are perfectly reversible. Yet I am one-sided. I speak and the voice goes out into the air and doesn't come sucking back into my mouth when I open it. This irreversibility cannot be blamed on obscure particle physics. It's everywhere all the time in everything, so we have to look elsewhere to find the explanation. Now, here's where it gets even stranger. You're realizing that everything you thought you knew was incomplete. That feeling, that mixture of excitement and frustration, that's growth. That's your brain rewiring itself around a deeper truth. The fundamental laws permit time to run backwards, but reality refuses. Why? How many other things do you accept without questioning? What else is hiding in plain sight, waiting for you to actually think about it? Let's look more carefully. If you examine planets moving around the sun with enough precision, you'll find something isn't quite right. The Earth's rotation on its axis is slightly slowing down. That's due to tidal friction, and friction is something obviously irreversible. If you push a heavy weight across the floor, it slides and stops. If you stand and wait, it doesn't suddenly speed up and come back into your hand. Frictional effects seem inherently one way. But friction isn't fundamental. It's the result of enormous complexity. The interactions of the block with the wood, the jiggling of atoms inside, the organized motion being converted into disorganized thermal wiggling. So we should look closer. And here we find the clue to apparent irreversibility. Take blue water, ink dissolved in water, and white water, plain water without ink, in a tank with a little separation between them. Pull out the separation delicately. The blue starts on one side, the white on the other. Wait. Gradually, the blue mixes with the white. After a while, the water is uniformly pale blue, 50-50 color distributed throughout. Now wait longer. Watch carefully. It does not by itself separate back into blue on one side and white on the other. Oh, you can do something? Evaporate the water, condense it elsewhere, collect the dye, dissolve it in half the water, put it back. But while you're doing all that, you yourself are causing irreversible phenomena somewhere else. By itself, spontaneously, it doesn't go the other way. Now suppose we took a moving picture of the blue and white water mixing. It would look absurd if we ran it backwards, because we'd start with uniform water and gradually the thing would separate, and that would be obviously impossible. But here's the key. Magnify the picture so that every physicist can watch atom by atom to find out exactly where the laws of balance between forward and backward break down. What do you see? You have atoms of one kind and atoms of another kind, all jiggling in thermal motion, wiggling and bouncing. At the start, most atoms of one kind are on one side, atoms of the other kind on the other side. These atoms are jiggling around, billions and billions of them, in perpetual irregular motion. If you start with all one type on one side and all another type on the other, they will obviously get mixed up through their constant bouncing. That's why the water becomes uniformly blue. But watch any single collision. Here's a particular collision selected from that picture. This molecule moves this way, that one moves that way. They come together and bounce off in different directions. Now run that section of the film backwards. You find a pair of molecules moving toward each other, bouncing off in different directions. And the physicist looks with a keen eye, measures everything, and says, that's all right. That's according to the laws of physics. If two molecules came this way, they would bounce that way. And if they came that way, they would bounce this way. It's completely reversible. If you watch too carefully, you can't understand the irreversibility at all. Every single collision is absolutely reversible. And yet the whole moving picture shows something absurd. In the reverse film, molecules start mixed up, blue, white, all jumbled together. And yet as time progresses through all these perfectly legal collisions, the blue separates from the white. They can't do that. That's not natural. The accidents of molecular motion won't conspire to make blues separate from whites. Yet every individual collision checks out perfectly. Think about that for a second. Every microscopic event obeys time, reversible laws. But the macroscopic phenomenon is completely irreversible. The explanation isn't in the laws. The irreversibility is caused by the general accidents of life. If you start with something separated and make irregular changes, it gets more uniform. But if you start with something uniform and make irregular changes, it doesn't get separated. It could. It's not against the laws of physics that molecules bounce around and happen to separate. It's just unlikely. It's so unlikely it would never happen in 1,000,000 years, in 1 billion years, in the lifetime of the universe. This should break your brain. The things are irreversible only in the sense that going one way is overwhelmingly probable, but going the other way, although possible and permitted by physics, is so fantastically improbable that it never happens. It's not impossible for a broken cup to reassemble. Every atom could, in principle, bounce in exactly the right way to put the pieces back together. The laws of physics would be satisfied at every instant. But the probability is so vanishingly small, 1 divided by a number with more zeros than there are particles in the observable universe, that you could wait longer than the cosmos will exist and never see it happen. Now here's where the implications cascade outward. If you had just a handful of atoms in a closed box, bouncing around forever, they would eventually, by pure chance, return to any configuration they'd previously been in. With 4 or 5 atoms, you might only have to wait a year. But the actual objects we deal with have not 4 or 5 atoms. They have 4 or 5 million atoms. And it's just not going to happen that 4 million atoms accidentally coordinate to separate themselves. We're about to connect everything. But before we do, ask yourself, are you the kind of person who actually follows through? Who takes knowledge and does something with it? Because what comes next isn't just information. It's a lens that will change how you see everything. And you can't unsee it. So the apparent irreversibility of nature doesn't come from the irreversibility of fundamental physical laws. It comes from a characteristic of starting conditions. If you start with an ordered system and let the irregularities of nature bounce things around, the thing goes one way, toward disorder. Always. Everywhere. Without exception. This raises the next question, the deepest question: how did it get ordered in the first place? Why is it possible to start with order? Because the difficulty is that we start with ordered things, and we don't end with ordered things. One of the rules of the world is that things go from ordered conditions to disordered ones. The word order here is technical. It doesn't mean beautiful or interesting or valuable. It just means a specific, definite arrangement versus a random, mixed-up arrangement. Ink on one side and water on the other is ordered. Uniform pale blue is disordered. Maybe you prefer the mixed color aesthetically, but that's not more ordered in the physical sense. Now the question is, how did things get ordered in the first place, and why, when we look at any ordinary situation that's only partly ordered, can we conclude it probably came from something more ordered? If you see a tank of water that's very dark blue on one side, very clear white on the other, with sort of bluish water in between, and you know it's been left alone for 20 or 30 minutes, you can conclude something remarkable. You can deduce the past. You know it was bluer before. The separation was more complete in the past. If you wait longer, the blue and white will become more intermixed. This is extraordinary. It means you can tell from the present something about the past. Physicists usually think they just need initial conditions to predict what happens next. But all our sister sciences work completely differently. History, geology, astronomical history, evolutionary biology, they all make predictions about the past. A geologist digs in the ground, finds certain bones, and predicts that if you dig elsewhere, you'll find similar bones. A historian says Napoleon existed, and what he means is that if you look in another book, if you find documents not yet discovered, they'll corroborate the story. How is that possible? The only way is if the past of the world was more organized than the present. Otherwise, you couldn't make such predictions. If the past were just as disordered as the present, there'd be no connection between documents, no pattern to fossils, no coherent history at all. Some physicists have proposed that the whole universe is just irregular motion, and if you wait long enough, fluctuations occur. Random accidents where things temporarily become more ordered, then fall back to disorder. Maybe we're just inside one of those fluctuations, watching it undo itself. How do we know that isn't the case? Well, you'd have to wait an incomprehensibly long time for a fluctuation big enough to produce evolution, intelligence, observers who could notice. So maybe we had to wait exactly that long. But this theory is wrong, and here's why. If the world were a fluctuation, if our little pocket of order emerged randomly from a vast sea of disorder, then the most likely configuration everywhere else would be maximum disorder. You can't borrow too much order in one place without paying for it somewhere else. If you notice something unusually ordered here, the most likely state everywhere else would be completely mixed up. But when astronomers look at stars they've never seen, they find the same kind of order. The separation of matter into hot stars and cold space, galaxies and voids, structure and emptiness, it extends everywhere we look. Every time we examine a new region, we find the same patterns. Every time we make predictions about places we haven't observed, those predictions come true. The success of all the historical sciences, the fact that we can reconstruct the past, that documents agree, that fossils form coherent sequences, that stellar evolution makes sense, indicates that the world did not come from a random fluctuation. It came from a condition that was more separated, more organized in the past than at the present time. So now what? You've just spent these minutes fundamentally changing how you understand reality. That's not nothing. That's rare. Most people never have this experience. The question is, will you remember this tomorrow, next week, or will it fade like everything else you've learned and forgotten? There's a way to make sure it sticks. There's a way to prove to yourself that this mattered. Here's where we have to add something to the physical laws. The laws themselves are time symmetric. They don't prefer past over future, but the universe does. So we must add a hypothesis that isn't derivable from the equations in the past. The universe was more ordered, in the technical sense of lower entropy, less mixed up than it is today. This statement is itself lopsided in time. It says something about the past that's different from the future, but it comes from outside what we ordinarily call physical law. It comes from cosmology, from the initial conditions of the Big Bang.
Atlantis on its way.
The early universe was extraordinarily smooth, extraordinarily uniform, extraordinarily low in
dynamic pressure.
Why, we don't know. That initial condition is one of the deepest mysteries in all of physics. The laws don't require it. Nothing we understand explains it. Yet without it, there would be no arrow of time, no irreversibility, no memory, no causation, no difference between before and after. Let me make this concrete with a thought experiment that illuminates exactly how irreversibility works even when every component is reversible. Suppose you build a wheel with a ratchet on it, a notched wheel with teeth like a saw. There's a little piece called a pawl held down by a spring that catches in the teeth. This wheel can only turn one way. If you try to turn it backward, the teeth jam against the pawl. If you turn it forward, it clicks over the teeth easily. They use these in watches and clocks. Now here's the clever idea. Because of molecular motion, the perpetual jiggling of atoms, molecules are always bumping into things irregularly. If you build a very delicate instrument, it will jiggle from being bombarded by air molecules. So connect vanes to this ratchet wheel and put them in a box of gas. The molecules bombard the vanes irregularly, pushing them sometimes one way, sometimes the other. When they're pushed backward, the ratchet jams. When they're pushed forward, the wheel clicks around. So the wheel should perpetually turn in one direction. Perpetual motion from molecular jiggling, free energy from thermal motion. But look at the details. When the wheel turns, the pawl lifts up and snaps back down against the next tooth, and it bounces. The wheel could go backward when the pawl accidentally bounces up. This mechanism won't work unless the pawl sticks when it comes down, and that requires friction, and friction generates heat. So this part of the mechanism gets hotter. But now something crucial happens. Just as there's irregular motion in the gas making the vanes jiggle, the pawl itself, getting hotter, starts jiggling from molecular motions inside it. A time comes when the pawl is bouncing up and down so much from its own heat that when it's up, a tooth can slip either way. The mechanism equilibrates. Once both sides reach the same temperature, the wheel goes in either direction. It just sits there, jiggling randomly, accomplishing nothing. This is the technical demonstration that phenomena of nature only go one way as long as they're out of equilibrium. As long as one side has a different temperature than the other, as long as one region is more ordered than another. The conservation of energy says nature never loses or gains energy. Yet the energy of the sea, all that thermal motion of atoms, is practically unavailable to us. To make energy useful, to make it available for work, you need a difference in temperature, a gradient from order to disorder. Without that difference, although the energy is there, you cannot extract it. Here's an analogy. You go to the beach with towels. A sudden downpour comes. You grab the towels and run to the bathhouse. You start drying yourself. This towel is a little wet, but drier than you, so it helps. Then you try another, but it's too wet. It's wetting you as much as drying you. Pretty soon you discover something horrible. All the towels are damp and so are you. No matter how many towels you have, there's no way to get drier, because there's no difference between the wetness of the towels and your own wetness. When everything reaches the same dampness, you're stuck. Temperature is like dampness. When two things are at the same temperature, it's just as easy to pick energy off one as the other. Put them together and they exchange energy back and forth, but the net result is nothing useful. When everything is at the same temperature, there's no more available energy to do anything. The universe is running out of temperature differences, out of gradients, out of useful disequilibrium. This is the entropy law. Entropy always increases. Or to say it another way, the availability of energy always decreases. Things of different temperatures left to themselves tend to become the same temperature. But two things already at the same temperature don't spontaneously split apart, one getting hot, one getting cold. The one-wayness is always the loss of available energy, the running down of gradients, the mixing up of differences. So let's bring this all together. Why can't we reverse time? Why don't broken cups reassemble? Why doesn't mixed ink separate? Not because the laws of physics forbid it. Every collision, every interaction, every force works perfectly in reverse. The reason is statistics, probability, the overwhelming number of ways things can be disordered compared to the tiny number of ways they can be ordered. A cup has one way to be whole, millions of ways to be broken. When it breaks, it moves from one ordered state to one of millions of disordered states. That's likely. That's what statistics guarantees. But for it to go back, for millions of atoms to accidentally coordinate perfectly, to reassemble, it's not impossible. Just so unlikely it will never happen. Not in the lifetime of the universe. Not in a trillion lifetimes. The deep truth, the universe started ordered. The early universe was highly organized, low entropy, smooth and uniform in ways we still don't fully understand. And ever since it's been falling apart, getting more disordered, more mixed up. Entropy increases always, everywhere. That's the arrow of time. That's why you remember the past and not the future. Why causes precede effects? Why you age? Why things break and don't unbreak? Why the cup shatters and never reassembles? The universe is running down, and nothing in the fundamental laws requires this. The laws work the same forwards and backwards, but the universe started ordered. That initial condition, unexplained, mysterious, sitting outside our equations, makes time flow in one direction. We don't know why the universe began that way. We may never know. But that's the answer to why yesterday is different from tomorrow. And this process, this avalanche of discoveries about time and entropy, started with Galileo figuring out how things fall by timing balls rolling down inclined planes. Then Newton figuring out that the same gravity that pulls apples pulls the moon, with universal laws that work identically forwards and backwards in time. Then Carnot and Clausius figuring out that heat flows from hot to cold and never reverses, that engines have fundamental limits. Then Boltzmann figuring out that entropy is about probability, about the number of microscopic arrangements compatible with a macroscopic state. Then Einstein figuring out that space and time are woven together, that the fabric of reality is stranger than anyone imagined. Then thousands of experiments confirming every prediction, measuring every effect, each discovery built on the last. Each new insight opened doors to more insights. That's how science works. That's the avalanche that's been going on for 400 years, and we're still avalanching along at high speed. Yet we still don't know why the universe started ordered. That question remains tantalizing and unanswered. Here we have an example where an obvious effect, the irreversibility of time, the most fundamental feature of our experience, is not an obvious consequence of fundamental laws. The effect is far from the basic equations. It takes enormous analysis to understand why. And the effect is of first importance. Your memory, your characteristics, the difference between past and future, your entire existence as a being embedded in time, it's all involved in this. Yet understanding it isn't immediately available just by knowing the laws. The laws of physics don't have direct, obvious relevance to experience. There are often great distances between detailed laws and main aspects of real phenomena. Like a glacier, you watch it move, rocks falling, ice flowing. You don't need to know it's made of hexagonal ice crystals. Yet the character of those crystals, if understood well enough, is the reason for the glacier's motion. But it takes time to connect them. In fact, nobody knows enough about ice crystals yet to fully understand glacier behavior. And nobody knows enough about cosmology to fully understand why time has a direction. Although we've been talking about fundamental physics, knowing all the fundamental laws doesn't immediately give you understanding of much. It takes time, and even then understanding is only partial. Nature seems designed so the most important things in the real world are complicated accidental results of many laws working together. The irreversibility of time isn't fundamental, it's emergent. It arises from statistics applied to initial conditions we don't understand, and that makes it both more mysterious and more beautiful. The arrow of time, the thing that makes you who you are, that distinguishes your memories from your hopes, that makes the past fixed and the future open, it's a cosmic accident. An accident of how the universe began. An accident we're still trying to understand. You know what separates people who truly understand science from people who just consume science content? Action. The ones who understand do something with it. They engage, they question, they discuss, they challenge. They don't just passively absorb, they participate. Which one are you? Time isn't just something that passes. It's the key. It's the thing that unlocks how causation works, how memory works, how the universe evolves from simplicity to complexity, and then back toward the heat-death of thermal equilibrium. It's the thing that shows us reality is stranger and more beautiful than we ever imagined. And the fact that we can understand it, that we can measure entropy, test predictions, trace the arrow of time back to the Big Bang, that's the beauty of physics. Not comfort, not simplicity, not easy answers that fit in a tweet. Truth. Deep, strange, hard, one truth about the nature of existence. If you made it this far, you're part of a small group. The group that doesn't settle for simple answers. The group that wants to understand, not just know. And here's what I've learned: people like you, people who think like this, they find each other. They recognize each other. They build on each other's understanding. That's how the avalanche continues. That's how we keep discovering. Not alone, together. The arrow of time points forward, and so do we, toward more understanding, more insight, more of the truth that makes the universe comprehensible to beings like us, brief flickers of ordered complexity in a cosmos slowly running down.